Riemann hypothesis proof. In mathematics, the Riemann hypothesis is a conjecture that the Riemann zeta function has h0 only at the negative even integers and complex numbers within real part 1/2. Many consider it to be the most important solved problem in pure mathematics. It is of great interest in number theory because it implies the result about the distribution of prime numbers. It was proposed by Bernard Riemann, after whom it is named. Now let's prove Riemann's hypothesis. First, main result. Dimension of a sphere with volume divergence. Notification. S3D is a sphere with volume divergence, and DS3D is a boundary of a sphere with volume divergence. And SV1 is a sphere with volume 1, and DS3-1 is a boundary of a sphere with volume 1. First theorem. If DS3D exists, DS3D is homeomorphic with 4-dimensional Euclidean space. If DS3D exists, DS3D is homeomorphic with 4-dimensional Euclidean space. 4D Euclidean space is a metric space with 4 independent variables, and this is a usual 4-dimensional space, we can usually say. So we can say DS3D is 4-dimensional. Let's prove it. To show they are homeomorphic, we must show first that there is a function from DS3D to 4-dimensional Euclidean space, and the function should be one-to-one correspondence, and both the function and its inverse function should be continuous. To do that, we've defined the spherical coordinate inside the S3D and assume 3 independent vectors which originate in the center of S3D. And in orthography and normalization, these vectors can make a rectangular coordinate system, and this 3-dimensional rectangular coordinate system can be translated into 3-dimensional spherical coordinate. Now, in this spherical coordinate, you can define an angle theta phi. And within this angle, we can project the point from the center of S3D to DS3D. Then I can call the projected point as S theta phi, and we will call this point as A. First, we will show that DS3D has 4 independent variances. And I will call a point near A, which is on the DS3D as B, and then B is on the surface. So to express B, I can use polar coordinate which originate as B. A, so B is expressed as omega L, where L is finite length from A, and omega is an angle which specifies a specific point within distance L from A. And to express B, we first define A. So B is expressed as theta psi omega L, which is a sum of coordinate of theta phi and omega L. Now we will show the 4 coordinates are independent. So we should show that theta psi is independent with omega L. First, L, we will show that if L can be expressed with theta psi, then there exists a contradiction. Assume L was expressed with theta psi, and the equation expressing the area of DS3D is 4 pi r squared. And R is infinite, so the area of DS3D should be infinite. And if we express the area of a circle inside, it is 4 pi r squared. This is arrived at by multiplying the radian to the area of DS3D, but the multiplying number is infinite value, produces infinite value. But the area of circle within the radius R is finite. So there is it the contradiction when we assume R is expressed with theta psi. So R and theta psi are independent. Now we will show that omega and theta psi are independent. First, assume omega can be expressed as theta psi, and assume a function like this. And R is a length value in spherical coordinate of S3D, and Ri is a length value in spherical coordinate of S3-1, and theta psi is the angle value in spherical coordinate of both systems, and it satisfies this. And R is the length from origin in the S3D system, and I is the length from origin in the S3-1, and F is a function which goes from sphere to sphere, so the angular value of zeta psi on the boundary of a sphere is conserved within F, and within F the length value is conserved with regard to the small and large relation. And with F, the final circle in the dsVD goes to a point in the dsV1, which we will prove now. The value of delta zeta delta psi is conserved in the F because F conserves the value of zeta psi, and the final circle on the dsVD is always smaller than 4 pi r squared delta zeta delta psi, which is infinite. And because zeta psi is conserved in F, so the value of 4 pi r squared delta zeta delta psi in dsVD becomes 4 pi delta zeta delta psi within F. So F value of the final circle on the dsVD should always be smaller than 4 pi delta zeta delta psi, and the circle which is smaller than every other circle is a circle with zero size. So the circle which has final F value on the dsVD goes to a point on the dsV1. And here, omega is an angle value which pertains a point on the boundary of the circle, and we assume omega can be expressed with zeta psi, and F conserves zeta psi. Then when a final circle on the dsVD goes to a point on dsV1 with an F, the omega value which is expressed as zeta psi conserves. So then the point on the dsV1 should have omega value which is expressed as zeta psi. And the function f has inverse function like this. This means a point goes to two-dimensional field with inverse f, and is contradiction to the fact that f is one-to-one correspondence and has inverse function. So omega and zeta psi are independent. So zeta psi omega L expressed on dsVD are four independent variables. This means a point goes to two-dimensional field with f inverse, and it is contradiction to the fact f is one-to-one correspondence and has. Yes, yeah, I said it. Okay. And consider the next function. Like this. And its inverse function is like this, that. Then f is a function from dsVD to four-dimensional Euclidean space. It has one-to-one correspondence and is continuous. And f inverse is a function from four-dimensional Euclidean space to dsVD, and it has one-to-one correspondence and it's continuous. So dsVD is four-dimensional manifold. Now I'll explain theorem 2.1.2. Bulk of SVD is five-dimensional. We will use Poincare definition. Let's see the definition about dimension by Henri Poincare. One dimension is a zero-dimensional section, two dimension is a one-dimensional section, and three dimension is a two-dimensional section, and four dimension can be defined as a body whose section is three-dimension. And by mathematical induction, five dimension can be defined as a body whose section is four-dimensional. Now let's put this definition to theorem 2.1.1. dsVD is a section of SVD, and dsVD is 4D manifold. So the bulk of SVD is five-dimensional. Next, I will see theorem 2.1.3. A circle with finite area on a dsVD is a plane. dsVD has a curvature as 1 per r. R is the radius of a sphere, and r has an infinite value, so the curvature of SVD is 0. So the final circle on the dsVD is on the plane. So we proved the sphere with volume divergence is five-dimensional and the surface is 4D plane. Next time I'll prove black hole is a sphere with infinite curvature, so black hole has 4D plane surface and 5D bulk. And this way I will prove ADCFT correspondence theory in a mechanical energy.